We discussed in this video about grammars and we mentioned them in the beginning of the course, and the original motivation for the study of grammars, at least in the sense that we mentioned them in this course. So the original motivation was for the grammars to be linguistic, or if you like, really mathematical structures to generate all sentences, I should say all correct sentences of a language, and I would say here of a human language, whether that's a natural language or a programming language or something. But you have a language and you have sentences in that language, and the goal was to have a structure that generates all of these languages. And this original motivation goes all the way to Chomsky, 1956. And the stress in this part of the course is really on generating devices. So this is going to be about generating devices. And they are very different than the other devices we have seen in this course, which were accepting devices, or if you like, computing devices. Meaning that we have seen automata, and the automata, they had an input, and on those inputs they were doing a computation, and then in the end they were accepting or rejecting. The generating devices we will see, meaning the grammars, they don't have an input, but they produce an output, and the language of a grammar is going to consist of all the outputs that grammar can generate. So they go in a different way. This one has an input and they accept or reject, and this one really generates a word. And I will give you the formal definition. So a grammar, so this is a structure of the following type. You have V, sigma, E, and S. And I explain the meaning of each one of these components. V is an alphabet, meaning a finite set. So V is an alphabet of symbols. And there really are two different categories of symbols. One is terminating symbols, and I will comment in a moment about what exactly does it mean, terminating symbols. But these terminating symbols, they are those collected in set sigma in the definition. And the other ones, I should say terminal symbols. I'm sorry about that. So terminal symbols, and they are collected in sigma, and then the other category is non-terminal. And we just have all the other ones, V minus sigma. And then we have, maybe I mention just S. S is the starting symbol. And again, I mean, I will define in a moment what does it mean starting. But in any case, S is always a non-terminal. So S is always a non-terminal. And P is the set of productions. And what this means is really it's a set of rewriting rules. So a production is simply just a rewriting rule of the type alpha goes into beta, where alpha is something that has at least one non-terminal. So you can have whatever symbols you like, there's got to be at least one non-terminal. And beta can be, whatever, over V star. It can have non-terminals, it can have only terminals, it doesn't really matter. But on alpha, you have got to have at least one non-terminal. So there you have it. V is the alphabet of symbols, and there are two types, terminals and non-terminals. and you have a starting symbol, and you have productions, and productions are of this type. Alpha goes into beta. And we have the notion of a derivation. So I'm going to say that word U from V star derives, and this is on the concept of derivation. So derives word V if we have something like this. So I'm going to say also the notation. So this is denoted by U, and this double arrow, it means U derives into V. If we have something like this, U is of the form U1 alpha U2, V is of the form U1 beta U2, and alpha goes into beta is a production. So what this means is that you will have a derivation from U to V if simply somewhere inside U you have an alpha which is being replaced by beta. The rest of the word remains unchanged. You had a U1 in here and U1 stays unchanged, and U2 in here, U2 stays unchanged. And this is done via productions of this grammar. So word U derives a word V if you find the left-hand side of a production, and as a result of the derivation, you replace that left-hand side with the right-hand side of that production. And so this is, in some sense, derivation in just one step. And then we say this the notion of derivation is extended to multiple steps. So not just as a result of a single rewriting, a single production, and we will say something like this. So in this case, we will denote it U derives V, and we put star in here because it can be as a result of many steps. If you simply start from U, so let's say this is a maybe this is, we just call it W0, and this one derives, just like we had before, into something like W1, and this derives into a W2, and so on. You have a sequence of these steps, and then at the end you get the word you wanted, which is V. So we will just say that this is a derivation now in multiple steps. And we also have this agreement that by default we always say that U derives U. So this is really in 0 steps. You don't have to do anything, but we include it by default in this notion of derivation. And now we are ready to define the language generated by a grammar, and we do it in the following way. So again, we have a grammar G made of this alphabet, and these are the terminals. That's the set of productions, and that's the starting symbol. And we will say the language L of G generated by grammar G is this set. And there are a few things that I want to draw your attention. So I'm first writing it, and then I explain. So what this definition says is these are words where you have only terminal symbols. And this is now the place where I explain what these terminal symbols are and what non-terminals mean, and I do that in a second. And the second part of this definition, it says that derivations So or productions of these output derivations always start from the so-called starting symbol S. So there you go. The idea that this would be called a starting symbol is because you always start these derivations of your words in the language, you always start from S. So that's why this is called a starting symbol. And you only want words that are made of terminal symbols. So terminal symbols are those that you don't need to really replace anymore in your derivations. And that leaves the non-terminal symbols to be thought of. So the non-terminal symbols, really you should think about them as sort of intermediary symbols that are going to help you on the way from the starting symbols to the word that you want to generate. So in some sense they are really helpers, but in the end you only want words over your terminal symbol. So sigma is really the alphabet that you are interested in terms of the words that you are generating. I would also like to draw your attention to something else, and that is if you have a derivation. So if you have a grammar and a word from the language of this grammar, so a derivation for W. So derivation for W could be something like this. S is really going into something like alpha 1, and then this goes into alpha 2, and so on. So this goes into eventually something like alpha n, which is really the W. So this is going to be called a derivation for W. And we also can represent this in terms of derivation trees. You can see this if I'm writing all the letters of alpha 1, so maybe they are x1, x2, xm, and these can be terminals or non-terminals. So derivation trees, this could be like this. S is really going into, I'm just showing all these symbols, x1, x2, all the way to xm. And some of these are non-terminals. If this one is, for example, a non-terminal, and that's the subject of the second derivation, and I'm just going to show it on this derivation tree. How is this being replaced? And also maybe this one is going to be replaced at some point. Maybe this was a non-terminal, and we show this, and we just develop this. And some of these, maybe this one was a terminal, and so obviously this one doesn't get replaced. But so we just continue with these, and at the end we check the produced word by checking all these terminals that we have in the different parts of the tree. So we are going to check all these symbols that are here at the leaves of the tree. So this will become a little bit clearer in a moment when we give a few examples. But I just want to introduce this notion of derivation trees. These are also called, especially in computer science when it comes to programming languages, these are also called parsing trees. So for a program that you're writing, there will be a parser, and that parser will tell you if you have any syntax errors. So they might give you some message about your syntax being wrong. And that's exactly where grammars are really good. They can give you messages about your syntax being wrong. You wrote the program in a way that really violates the rules of that programming language, of the grammar that's behind that programming language. And in the next video, we are going to see a few examples of grammars and of derivations.